This is lecture 10C on the arc length and surface area for parametric equations. To find an expression for the arc length for parametric equations, we'll do the usual, what we usually do in calculus, and that's we start dividing things up into little sections and taking the limit. So we're going to take this curve and we're going to divide it into little sections just as we did before when we were developing the expression for the arc length in general. Alright, so we have the length of this little section, which we're going to approximate as linear. The length squared equals delta x squared plus delta y squared. Right. And the parametric equation, both x and y are functions of this parameter, which we're going to say is t. And then we're going to use the mean value theorem. Okay, the mean value theorem says that in each little subsection there is some value of t where the derivative along the curve in the subsection equals the mean derivative, which would be the average derivative, dx by dt, delta x over delta t. Similarly, for y, there is some value of t, we're going to call it t sharp, where the derivative along the curve equals the average derivative. So this is all we've done, is use a mean value theorem for derivatives. Then we're going to rearrange a little bit and find a new expression for delta x. Delta x is the time derivative of x times delta x, and delta y is the time derivative of y times delta t. And we're going to substitute that. The substitution, now we have an expression for this length in terms of the parameter t. So we're going to add up all these little tiny lengths, and in the end we're going to take the limit. So here is the limit. Of course, we're taking the square root first because we don't want L squared, we want the actual length squared. And now we have the length along a parameterized curve. We can take the derivative over the parameter t from t1 to t2. Those are the two times of interest, and the curve is being traced out between those two times. It's the square root of dx by dt squared plus dy by dt squared. The arc length function follows immediately. The arc length function, it's a function of t. And now we're integrating from t1 to some arbitrary time t. We have to change, remember, change the dummy variable under the integral sign, so I'm using ta here. Okay. And we also have an expression for the arc length differential that we'll use when we look at surface area. Just as in the case for arc length in general, very few curves have arc lengths or arc length function with closed form solutions. Now we want to look at the area beneath a parametric curve. If we wanted just the area in Cartesian coordinates, we would just integrate from x1 to x2 of y of x dx. That's just the definite integral, that's all, and we find the area beneath the curve. But here x is a function of time, and so is y. Well, y of t can be substituted, and instead of dx, we want to integrate with respect to time. dx by dt times dt gives me a dx. Using that substitution, we can now integrate from t1 to t2. We just use the change of variables, that's all. And then we integrate with respect to time, which is handier, actually is required if we have x as a function of time and y as a function of time. So what we're doing is just running down the list of the derivative, surface area, area beneath the curve, arc length, everything that we did for functions in general, we're now applying to these parametric equations. So we come now to the surface area for a parametric equation. Here was the expression that we developed before for curves in general, in the Cartesian plane in general. We integrated between several values of x of 2 pi y. Remember, this is a figure of revolution, so the cross-sectional area is a circle. That's where you get the 2 pi here. So I've got 2 pi y times the arc length. Alright, that arc length differential. Here was our arc length differential for the parametric curve, and it's immediate. Y, again, is a function of time. So now we have the surface area for a figure of revolution in terms of the parameter t. And now I'd like to summarize all these results in 2 slides, because when you see them all together, they sort of make sense. When you see them independently, it's like, well, okay. So we have a set of parametric equations, x of t and y of t, and the parameter we're going to use is t for these discussions. So we need the first derivative. This is the derivative along the curve in the Cartesian plane. So dy by dx equals dy by dt divided by dx by dt. That slope will be vertical, actually undefined, when dx, these numbers are mixed up. Alright, I fixed my slide, so here's my summary. So we're summarizing the equations that we developed for parametric curves. That is, curves in which x and y are both functions of a third parameter, or a third variable we call the parameter. In this case, we'll let t be that parameter. The first derivative, this is the derivative of the slope in the Cartesian plane, in the xy plane, is equal to the ratio of the time derivatives of the functions. So dy by dt divided by dx by dt. This slope is undefined, or you might draw a vertical line there, when the denominator d by dx is equal to 0, but the numerator is not 0. The slope is horizontal, in other words, it has a value of 0 when the numerator is 0, but the denominator is not 0. The second derivative has this form. It is equal to the time derivative of the first Cartesian derivative, right, divided by dx by dt. And here's an expression for the arc length function. It's the integral from t1 to t. Again, we're writing everything in terms of that parameter t times the square root of the first time derivative of x squared plus the time derivative of y squared. The enclosed area for the times t1 to t2, that means the area that's swept out in the time t1 to t2, is y of t times the first derivative of x times dt, and here's an expression for the surface of revolution. Surface area for a figure of revolution if it's generated by some parametric y of t.